Hello everyone, welcome back to Pallence AI. In the previous video, we did a deep dive into how recurrent neural networks actually work for sequence data. The memory concept, how we can unroll an RNN through time, and the math behind it. Now in this video, we're going to take this understanding one step further. See, first of all, RNNs are not one size fits all, depending upon the type of problem we are solving. Let's say for sequence data related to language or NLP, right? Whether it's sentiment analysis, name entity recognition, question answering, translation, or even text generation, resulting RNN network can look quite different. So today we're going to take a deeper look at these different types of RNN architecture, again dealing with different types of NLP problems. And I'm going to walk through each of this with a clear diagram so you can actually see the difference. And by this end of this video, hopefully you'll have a complete mental map of how RNNs can be structured for different real-world NLP problems. That mental map is going to be extremely useful when we later move into more advanced architectures like LSTMs and eventually transformers. You can watch this video on its own, again, if you have some understanding of deep learning or RNN, like the previous video. But if you're completely new, I would encourage you to start from the beginning of the playlist, or at least the previous video in the playlist. All right, now let's look at different types of RNNs. Okay, all right. The first would be a sequence to sequence kind of RNN, the one which we just looked at. For example, for the token classification or named entity recognition. What do I mean by sequence to sequence? Well, our input data is a sequence, right? X1, X2, X3 up to XT. It could be a time series, like, stock price at different times, or it could be human language, like English sentence. That's a sequence. Now, given a sequence, you want to predict a sequence, meaning for every time step, you want to predict a Y. So Y1, Y2, Y3, YT, that's also a sequence. So if you given a sequence, you want to predict a sequence, that's called a sequence to sequence type of network or RNN. Okay. Example is named entity recognition, like we have already seen. So if you give this sentence, you want to predict for each word what the Y is. So I haven't shown the Y for like founded, headquarters. That would be a category called O, let's say, other category. But for every word, you predict what its class is, what entity it belongs to. Okay, so something like this. So this is an example of a sequence to sequence network. Then you have a sequence to vector. Okay, so for example, for sentiment analysis. So what is a sequence to vector? Again, my input data, input sample is a sequence. Okay, let's say you give us some sentence here. So given some sentence, you want to predict whether the sentiment is positive or not negative. So what we are doing now is we are not trying to predict the output at every time step, right? Because if you see, for example, a sentence like this, once in a lifetime experience to watch this masterpiece, there's a typo here, but once in a lifetime experience to watch this masterpiece. Let's say, given this sentence, we want to predict the sentiment and it's positive. So you want the model to read this entire sentence and predict that it is positive. So you don't want any output for every token, every word. You just want one output at the end. And that would be a sequence to vector kind of RNN. Okay. Or then you can use something called vector to sequence. Okay. What is a vector to sequence? So here, our input is not like, some kind of a sequence. Okay. This is particularly useful for music or text generation. So for example, let's say we just want to give the word mystery. So we'll just give one word, mystery, and you can represent this mystery through some kind of, just represent the mystery word through some kind of a numeric vector. That's what I mean by vector. So if you just give this mystery word to our RNN model and we say, hey, can you come up with some kind of a, can you generate some text using the word mystery in it? And our model will return something like this. Mystery shrouded the old Hamilton street where whispers told of vanished souls. It just generated some text using mystery as a prompt. Okay, so this would be a vector to sequence kind of network. Okay, or then you could have something called encoder decoder type of network. Okay, so this is particularly used for translation type of task, language translation. So again, given the sentence input, the sky is blue, you want to predict the translation in Spanish. Okay. I just wanted to give you an idea of the different types of RNNs we can construct: sequence to sequence, sequence to vector, vector to sequence, encoder decoder. Okay, all right. Now it's time to look at each of these RNNs, let's start with very simple. I'm going to show you how we can build some simple RNN layers or networks, and then I'm going to branch out to some deep RNN networks. I want to show you, through these diagrams, network diagrams. I want to give you the intuition or a deeper understanding as to how these RNNs might look like. So hopefully once we start doing the projects, all this information will really help you. Okay. All right. So first we're going to construct an RNN layer with just one hidden unit. So previously I showed you RNN with 5 hidden units, right? Now I'm going to construct RNN layer with just one hidden unit. Okay. How does that look? Very simple. Something like this. Again, my input data is a sequence. Let's say I'm using 30 time steps here. Okay. X1, X2, X3 up to X30. Okay. And you have a A0. A0 will be 0. Initially it will be 0. Okay. So as you can see here, whatever input you give X1, you calculate A1, and from A1, you feed that A1 to the next time step. So you compute A2 using A1 and X2, you compute A3 using A2 and X3, and so on up to the end, and then finally you get the output A30. Here I have not added another unit on top of this RNN layer to compute Y at each time step. I haven't done that. So you could have something like this too. Whatever the this RNN layer outputs, that could be your output. So that's the reason I said A equal to Y. The final A30, or basically I should say A30 equal to Y. Okay. So this is a simple RNN layer with one hidden unit. So again, if you see the RNN layer, right, inside the layer, there's only one unit. Okay, very simple one. Previously, I showed you with 5 hidden units, but right now it's just one. So you could have something like this. And this would be a sequence. So you are giving it a sequence and you're predicting a vector. Basically, you're just predicting the final output, this A30. That could be a vector. Okay. And each X1 at each time step could further be a multi-feature vector or matrix. Remember what I said? If it's an English language, each X1, how are you going to represent that? Elon, let's say the word Elon Musk or Elon, we will represent each word, right, as each English word as a numeric vector, something like this. Or if it is a time series, right, so each X1 again could have different units here or features here. Again, you will understand that once we start doing some projects in time series more clearly. But hopefully you understand the explanation with respect to English language. Okay, so each word is represented as a numeric vector. Okay. All right. So now let's do another simple RNN. It's also going to be a sequence to vector, but now we're going to use RNN layer with multiple hidden units, just like I've shown you, earlier. So instead of one unit in the layer, we are having multiple units at each time step. You can see that, right? Okay. And once again, this is a sequence to vector because at each time step, I'm not outputting any Y here. But in the end, once I get this A30, I'm going to compute, I'm going to put one more unit there and I'm going to compute this Y30. Basically, Y30 means I'm just trying to compute the output, the final output only at the last time step. Okay. All right. So this is also a sequence to vector, but it's an RNN layer with multiple hidden units. Okay. And then we have a dense layer with one output unit at last time step. Okay. All right. So now let's look another one. This is also a sequence to vector. Okay. But this time what we're doing is, it's also a RNN layer with multiple hidden units. But at the last time step, instead of just one unit, we have a dense layer with multiple units at the last time step. So you may ask, what are we doing here? Once we had for example, if we go back here, like I'm just going back here, we just have the output of the RNN. That's it. Then we put like one unit here, right, on top of A30 to compute this Y. Okay. And then now I am putting multiple units to calculate, in the final layer for the Y. So you may ask, what are we doing here? Well, it depends upon the problem. What are we trying to output in the end? What are we trying to predict, for our task? So I'm just showing you these networks right now, but very soon we're going to start working on some hands-on projects. So there also I'll use the schematics again to explain, what kind of output we actually calculate and why. Okay, hopefully that gets clear. But for now, I just want to show you these different types of RNN architectures. And then we could have a very deep RNN. right? So, you could have something like this. So, bottom line, we have our input sequence, and what we're doing is we are having multiple RNN layers here, not just a single RNN layer. We have multiple RNN layers stacked on top of each other. Again, at each time step, we are not predicting any output or any final output. We are going to predict this Y only at the last, after the final time step, right? Whatever the output comes out of this last RNN layer, on top of that, we're going to use one more unit and calculate this Y. Okay, this is a deep RNN. Then we could have a deep sequence to sequence RNN. So now the only difference compared to the previous one, this was like this, and this one is now at each time step, right? At each time step, I am going to calculate this Y. Okay. Again, its RNNs are stacked on top of each other, and after the final RNN layer in pink, right, we have this final Y layer. So where we're going to calculate Y as a sequence at each time step. Okay, all right. We could also have a sequence to sequence 1D convolutional and RNN hybrid architecture, where for the first layer after the input sequence, we can do a one by one convolution with multiple filters. Okay, and on top of that we can use an RNN layer, and then on top of that we can use this final Y layer, and then compute the Y as a sequence at each time step. All right. So hopefully now you have a clear picture of the different types of RNN architectures, whether it's sequence to sequence, sequence to vector, vector to sequence, encoder decoder, and how all these translate into actual neural networks, again, whether it's with single layers, multiple layers, or very deep RNNs, or even hybrid CNN-RNN architectures. Now in the next video, we're going to move into something very important. We're going to look at the limitations of these simple RNNs. Specifically, what happens when the sequences get very long. And that's going to naturally lead us to LSTMs and GRUs, a more powerful evolution of RNNs that are still widely used today in real-world applications. And if this video helped you, please share it with anybody who wants to understand or master deep learning on a fundamental level. Okay, see you in the next video. Happy learning.